In this video, we're going to define one of the most important things in all of calculus. It's called a derivative. And just a warning for you, this particular video is going to be filled with a lot of tedious calculations in our examples. Eventually, we're going to learn an easier way to do these problems, but not yet. So this video is going to be a lot of fun for me, but maybe not quite as much fun for you. So hang in there and you'll get through it. We're going to start by talking about one particular type of problem that these derivatives that we're going to learn can help us solve. It's called the tangent problem. And so that is going to be our first focus, is the tangent problem. And here's an example using this problem. Find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. So first thing I'm going to point out before we even try to solve this problem is exactly what this tangent line is that they're talking about. This tangent line has absolutely nothing to do with the function tangent of x. So if you're thinking that just because you see the word tangent, try to get that out of your head. Tangent line is just a perfectly straight line that touches your graph at exactly the point specified. So for this particular problem, we have the parabola y equals x squared. Let me draw that out real quick. We know y equals x squared is just our nice parabola like this. And we have the point 1, 1 on this parabola. And we're talking about a tangent line to this curve at that point. That just means we're looking for the perfectly straight line. I'm going to call this line T for tangent line. That perfectly straight line that just touches the graph at the point that we want. Well, one thing we know back from all of our algebra and pre-calculus days is in order to get an equation of a line, you need a slope and you need a point. We have the point. The point is 1, 1. We need to find the slope. So we need to find the slope of t. But that's a little difficult to do right now because I have no information other than it hits the point 1, 1, and there's this parabola here that touches at that same point. Well, what we're going to do is we're going to estimate the slope by using a secant line of our parabola. Back in pre-calculus, you should have learned about a secant line. That's just the line that connects 2 points on your graph with a nice straight line. So for example, if I chose this point up here on my parabola, the secant line connects those 2 points. And you can see that particular secant line is not the best estimate for my tangent line, but the closer and closer we choose the point to 1, 1, the better it's going to get. So just in general, we're going to estimate using the slope of a secant line. So estimate using the slope of the secant line. Between our point 1, 1 and the point, just a generic point on our parabola, x squared. So the slope of that secant line is x squared minus 1 over x minus 1. So I know that the slope of my tangent line is approximately equal to this. We just have to plug in the value for x on the point that we're using for the secant line. Now, like I said earlier, this estimation of this tangent line is going to get better and better the closer this other point on my curve gets to 1, 1. And we have now learned something in calculus that allows us to evaluate things as we get closer to certain values. This is a limit. So if I actually want the exact value of this slope, I need to take a limit as my x value approaches 1 of this x squared minus 1 over x minus 1. This just means I'm taking this other point on my curve closer and closer and closer to the point 1, 1, and as soon as I get it all the way there, we're going to get the actual slope of this line. So we need to calculate this limit, which luckily we know how to do now. So I know the slope of my tangent line is equal to this limit as x goes to 1 of x squared minus 1 over x minus 1. If I were to plug the 1 directly in right now, I'd be getting 0 over 0. So we just need to do some algebra so we can simplify this. We're going to try factoring to figure this one out. If I factor the numerator, I have x minus 1 and x plus 1 on top with that x minus 1 in the denominator, and then I will be able to cancel my like factors. So I get the limit as x approaches 1 of x plus 1, and now when I use my direct substitution, I get that this is equal to 1 plus 1, which of course is 2. So now, this 2 right here is the slope of my tangent line that I was looking for. And now we can finally write the equation of the tangent line. All we need to write the equation of a line is a slope and a point. We had the point before, and now we have the slope. So I had slope is 2, and we had point 1, 1. So that means my equation of the tangent line, if I use point slope form, I get y minus 1 equals my slope times x minus 1. Or we can convert this to slope intercept form and get y equals 2x minus 1. Either way is perfectly acceptable. So there, we found our first equation of a tangent line without even having a very formal definition of how to find the equation of a tangent line. So now let's go ahead and write down a nice formal definition for how we find the slope of our tangent lines. So here's our definition. The tangent line to the curve y equals f of x at the point P, which is a f of a, is the line through P with slope m equals the limit as x approaches a, f of x minus f of a over x minus a, or the limit as h goes to 0, f of a plus h minus f of a all over h. These are two equivalent definitions here. It's just a matter of preference which one you would like to use more. I personally prefer the second definition, so that's the one that I primarily use. Think back to pre-calculus for a little bit. What I have right here, before I put this limit in the front, looks like an average rate of change, because it is. And what I had here, before I took the limit in the front, looks like our difference quotient, which you should have learned back in pre-calculus. So you should be fairly comfortable getting these two limits evaluated because it has things that you've done before. Let's do an example of another tangent line now that we have this definition here. So we are going to write the equation of the tangent line to the curve y equals 3 over x at the point 3, 1. So we know to write the equation of the tangent line, we need a slope and we need a point. We have the point, and now we have a way to find our slope. We know that by the definition, my slope is equal to the limit as h goes to 0, f of my a plus h minus f of a all over h. But now in this particular problem, what is my a that would be getting plugged in? Well, my a is my x value, so in this case it's 3. So we're using f of x as our y, and a is 3. So my slope is equal to the limit as h approaches 0 of f of 3 plus h minus f of 3 all over h. So now we just have to simplify this limit. So f of 3 plus h is 3 over 3 plus h. And f of 3, I could just plug the 3 into my formula, or I can use my point there and see that it's going to be a 1. So I have to evaluate this limit right now. And if you take a look at what we got, if I tried to plug that h in right now, we would have 0 over 0. So there is some work I need to do. I'm going to rewrite my numerator by writing it as one fraction up on the top. So I need a common denominator there of 3 plus h. So rewriting this, I would have a limit as h approaches 0 of, still have my h in the bottom, 3 minus a 3 plus h all over a 3 plus h, and all of that is over h. That again was found by getting a common denominator when I'm looking just at the terms on the top and writing it as one fraction. Now when I simplify this, I get 3 minus h over a 3 plus h. And instead of writing it as all divided by h, I'm going to write it as multiplied by 1 over h, just so that I don't have as many fractions to look at. And now let's see how this simplifies. I get a limit as h approaches 0 of negative h over 3 plus h times 1 over h. And this is some good news because my h's get to cancel out. They're a common factor. So now all I have to do to finish this limit up is find the limit as h approaches 0 of 1 over 3, or negative 1 over 3 plus h. Which now when I plug the 0 in for my h, I get negative 1/3. This is my slope. So now I can write the equation of my tangent line. Remember the point that we had to work with was the point 3, 1. So if I'm using my point slope form, where my point is the point 3, 1, we get y minus 1 equals negative 1/3 times x minus 3. Or if we convert that into slope-intercept form, you would get y equals negative 1/3 x plus 2. Either way is acceptable. All right, so now we've had a couple examples of finding a tangent line And we've had to use that pretty complicated looking limit definition, but we can handle that. We've had enough experience with limits now that we can handle those types of problems. Another type of problem we're going to be dealing with today is the velocity problem. So the velocity problem is obviously all about velocity. So the function f that describes the motion of an object is called a position function. And from the time interval t equals a to t equals a plus h, the average velocity is f of a plus h minus f of a all over h. If our h starts to go to 0, we, instead of getting an average velocity, get what's called the instantaneous velocity. So if h approaches 0, we get the instantaneous velocity, which is v of a equals the limit as h approaches 0, f of a plus h minus f of a all over h. So this is the instantaneous velocity at time t equals a. So this should look very familiar. This instantaneous velocity definition looks exactly like the definition for the slope of the tangent line. That's kind of interesting, but it's not a coincidence because both of these things are defined by the same mathematical concept, which after we do a definite example using instantaneous velocity, we'll actually get to that definition. So let's do a problem with this velocity first. So example, we will suppose that a ball is dropped from 450 meters above the ground. Using the equation of motion, f of t equals 4.9 t squared. What is the velocity after 5 seconds? So we are given a function that's representing the position of this ball. That's our position function. We want to find the instantaneous velocity 5 seconds after this ball is dropped. To do that, we need our definition of instantaneous velocity, which uses that limit. So what we are trying to find is the limit as h approaches 0 of f of a plus h minus f of a all over h. So here's my instantaneous velocity at just some generic value a. write down my definition again. And now I'm going to evaluate this v of a using this particular function. And at the very end, we'll plug in our 5 to figure out the velocity at time 5. So my function is 4.9 t squared. So when I plug that information into my formula, f of a plus h is 4.9 times a plus h squared. And f of a is 4.9a squared. This is all over h. And so I'm going to need to do a lot of distribution in the top. I get a limit as h goes to 0 of 4.9a squared plus 9.8 ah plus 4.9h squared minus 4.9a squared all over h. And now if I combine my like terms together, this 4.9a squared completely vanishes. And so I just have that 9.8 ah and the 4.9h squared left on top. So I have a limit as h approaches 0 of 9.8 ah plus 4.9 h squared all over h. But if I try to plug in h equals 0 at this point, I'm still at a 0 over 0 type of situation. So we still need to do more algebra. Looking at the top, I notice that I have an h in common everywhere. So I'm going to factor that h out. When I factor the h out of the top, that leaves a 9.8a plus 4.9h all over h, and then I can cancel my common factor of h. So we'll cancel out this common factor, and now I just have the limit as h approaches 0 of 9.8a plus 4.9h. And now if I plug in h equals 0, that 4.9h completely disappears, and I just get 9.8a. So what does this tell me? It tells me the instantaneous velocity at any value a is equal to 9.8 times a. The problem wanted us to find the velocity after 5 seconds, so all we have to do now is just plug in a equals 5, and we'll have the instantaneous velocity at 5 seconds. The instantaneous velocity after 5 seconds is 9.8 times 5, which is 49 meters per second. So at the very instant that it's been 5 seconds since the ball is dropped, the ball is moving at 49 meters per second. So we've now done a velocity problem using that strange limit with the f of a plus h minus f of a over h. We've also done tangent line problems using that same strange limit. The reason they both have the same weird limit in it is because that particular limit has a special name, and it happens all the time in calculus. That is our derivative. So let's write down our definition of a derivative. The derivative of a function f at a number a is the limit as h approaches 0 of f of a plus h minus f of a all over h. Or I'll write down the alternate definition, though, like I said, I like the one with h going to 0. That's the one I tend to use the most often. And it seems to be the more popular definition in general. But there is this other definition as well that we saw in our tangent line problems. But this is the one we will be primarily using. Now, the only thing I haven't said out loud on here is this strange notation at the beginning. It looks like f of a, but it has a little apostrophe in there, and that's pronounced f prime of a. This is just notation saying it's the derivative of my function evaluated at a. So this is f prime of a equals the limit as h approaches 0 of f of a plus h minus f of a all over h. So an example, just finding a derivative. Find the derivative of f of x equals x squared minus 8x plus 9 at the number a. Well, the first thing I'm going to do is write down my definition. My derivative, f prime of a, is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So now I just have to fill in what this actually is for this particular function. So I'm going to have limit as h approaches 0. My f of a plus h is a plus h squared minus 8a plus h plus 9. And then I have to subtract f of a, which is a squared minus 8a plus 9. And all of that is divided by h. And so now we need to distribute everything we can in the top and combine all of our like terms to see what we have. So when I do that, if I distribute everything on top, I'm going to have, let's see, we have an a squared, a 2ah, an h squared, minus 8a minus 8h plus 9. And then I have minus a squared plus 8a and minus 9. And all of that is still over h. So a good sign when you're actually finding your derivatives is at this point, you should have a lot of things subtract away to 0. And we do. If you take a look at this right now, I have a positive a squared and a negative a squared, so they subtract away. I have a minus 8a and a plus 8a, those subtract away. And my 9 and my minus 9. So let's see what we have now that we've combined those like terms together. Now we have a limit as h approaches 0 of 2ah plus h squared minus 8h all over h. And if you were to try to plug that h equals 0 in at this point, you're still going to have 0 over 0. So we need to find some other algebra to do. And just like the last problem, we're going to try to factor out an h so it can cancel with our denominator. When I factor out an h, I still have another 2a plus h minus 8. And now I can cancel my like factors of h. So all I have left now is a limit as h approaches 0 of 2a plus h minus 8. So now if I plug in h equals 0, all that happens is that middle term disappears, and I get 2a minus 8. So that is the derivative of my function at a. So this was f prime of a. All right, that was a lot of work, but it's a lot of work that we are familiar with, especially if you remember doing difference quotients back in pre-calculus. All that this is a difference quotient with a limit added into the problem. Let's do another example. Let's find the equation of the tangent line to the curve f of x equals x squared minus 8x plus 9 at the point 3, negative 6. So, like I mentioned before, your slope of the tangent line is equal to the derivative of our function at that point. We know that by just comparing all of our different definitions. So I know my slope is equal to f prime of 3, because my a value would be 3 in this case. So we would have to find the derivative at 3. Well, the good news is this is the exact same function that we just did in the last example. So we already know f prime of a is 2a minus 8. So all I have to do to figure out f prime of 3 is plug a 3 into that. So we get that f prime of 3 is equal to 2 times 3 minus 8, which is 6 minus 8, which is negative 2. So this is my slope. So now I have a slope, and we also have our point that was given to us, 3, negative 6, and now I can write the equation of the tangent line. The equation of the tangent line is given by y minus my negative 6 equals my slope times x minus 3. That's in point slope form. Or if you put it into slope intercept form, you would get y equals negative 2x. Either way is fine. I personally am a big fan of point slope form because once you have a slope and a point, you just put it in there and you're done. But sometimes you are asked to put things in slope intercept form, so it's always good to get that practice in. All right, so that was a good tangent line example. And so a summary of what we've learned so far. The derivative f prime of a is, well, it's the slope of the tangent line to the function f of x at x equals a. It is also the instantaneous rate of change of a function with respect to x when x is equal to a, and it is the velocity of a particle at time t equals a if f of t is a position function. So all of this is telling us that you could be asked to find a tangent line, you could be asked to find the instantaneous rate of change, you can be asked to find the velocity of something, and all of those problems involve finding the derivative. So now we're going to do even more with the derivatives. This is defining the derivative at a particular point, and the end result ends up being a number. But we can also define the derivative as a function. So here's our derivative as a function. Definition. F prime of x is equal to a limit as h approaches 0, f of x plus h minus f of x, all over h. This looks exactly like the definition we already know. It's just instead of having a number a, we're still using our variable x. And we're going to start with finding a derivative using this definition. So find f prime of x if f of x equals x to the third minus x. So the first thing we should do is just write in what this is by definition. I know that my derivative, f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And so for this particular function, f of x plus h is x plus h to the third minus x plus h, and my f of x was x to the third minus x, and this is all over h. So to find the derivative, I have to actually evaluate this limit. The first thing we should do is just distribute everything we can, so you'll have to write this x plus h to the third as x plus h times x plus h times x plus h, and do a lot of distributing. If you do all of that distributing, you will get a limit as h approaches 0 of x to the third plus 3x squared h plus 3xh squared plus h to the third minus x minus h minus x to the third and plus x. So that is doing all of the distribution on the top, but not combining my like terms yet. And this is still all over h. So remember, if you're calculating your derivative correctly, most of the time at this point, you're going to have a lot of things disappear. If we take a look, I have this positive x to the third and that negative x to the third. And I have a negative x and a positive x. So I do have some stuff that disappeared. Writing down what I have left, I have a limit as h approaches 0 of 3x squared h plus 3xh squared plus h to the third minus h all over h. And if you try to plug in h equals 0 at this point, you're going to get 0 over 0 again. So we're going to do the same thing we did on the previous problems, factor out an h from the numerator. So when I factor out that h, I have h times 3x squared plus 3xh plus h squared minus 1 all over h. Cancel our like factor. And now I just have to evaluate a limit as h approaches 0 of 3x squared plus 3xh plus h squared minus 1. So to do that, plug in h equals 0, and you'll see all of the terms that have an h in them disappear, and we just get our final answer for the derivative of 3x squared minus 1. So that is our final answer. F prime of x is equal to 3x squared minus 1. So that was a pretty long problem, but we were able to successfully find the derivative of that function using our new definition. Let's do another example, finding the derivative of a function using this definition. So find f prime of x if f of x is equal to the square root of x. First thing I'm going to do is write down my definition again. F prime is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And now we can plug in this information. So f of x plus h is the square root of x plus h. F of x is square root of x, and this is all over h. When I try to evaluate this limit right now, I'm going to get 0 over 0. But unlike our previous problems in this video, I don't have anything to distribute or factor or anything like that. So what should we do? We should try to multiply by the conjugate of the numerator. So I'm going to multiply this entire thing by square root of x plus h plus the square root of x over itself. Remember, on the top, that means you're going to have to distribute. And on the bottom, you should leave it factored as it is. Just write it all as one denominator. So let's distribute the top and see what we get. I would have square root of x plus h times square root of x plus h, which is x plus h. Square root of x plus h times positive square root x. And then my next term would be square root of x plus h times negative square root of x. So those subtract away to 0. And my last term is negative square root of x times square root of x, which is negative x. All of this is over h. I can then simplify. Don't forget the rest of the denominator down here. I was wondering what was going on. I forgot to write down the rest of my factored denominator. I have an h, and I also have square root of x plus h plus square root of x. So now if I simplify my numerator, my x's subtract away, and I just have h over h times square root of x plus h plus square root of x. And we're all set to cancel out that h in the denominator. So all I have left on top is another h. So I cancel my like factors. And we have a limit as h approaches 0 of 1 over square root of x plus h plus square root of x. Now let's see what happens when I plug in h equals 0. I would get 1 over square root of x plus 0 plus the square root of x. Well, square root of x plus 0 is just square root of x. So in the denominator, I have square root of x plus square root of x, which is 2 square root x. And so my derivative is 1 over 2 square root x. So we've successfully found another derivative. And now is a good time to tell you that for quite a bit of the rest of this course, we're going to just be doing lots and lots and lots of derivatives. So you can enjoy doing all of this by hand for most of the rest of the course. Though, like I already hinted, we will have some shortcuts and easier ways to do this. You just have to hang in there and get to the future videos that shows you the quick way to do some of these problems. I should warn you that there are other notations out there for derivatives. So if y is equal to f of x, then we have a lot of different notations. Our derivative that we're used to, f prime of x, can also be written as y with that little apostrophe, so y prime. This can also be written as dy over dx. That is not a fraction, so don't think about canceling out those d's. This is saying the derivative of y with respect to x. We can also write it as df dx, or as d dx of f of x, or a capital D of f of x, or a capital D with a little sub x of f of x. And there are even other notations out there. These are just some of them. I would say the most common notations that you're going to see are those three in the box right there. But you should be aware that there are other notations out there. So if you're looking at other resources, don't get confused. There's just a lot of different notations floating around out there. But the ones I have boxed up there seem to be the most popular in general. So what we have left for this video today is a definition, a theorem, another definition, and an example. So here's a definition. A function f is differentiable at x equals a if f prime of a exists. It is called differentiable on an open interval if it is differentiable at every point in the interval. So this is kind of a nice definition. It says that f is differentiable if the derivative exists. So if you can actually find the derivative, the function has this property of being differentiable. We have a theorem involving differentiable functions. That says if f is differentiable at a, then it is continuous at x equals a. And we need to be very careful with the statement of this theorem. This theorem is saying if the function is differentiable at a, so if the derivative f prime of a exists, then the function is also continuous at that point. This does not go the other way. This does not say if you are continuous, then you are differentiable. It only goes one direction. Differentiability implies continuity. So you might be wondering how a function can actually fail to be differentiable. And I'm just going to draw a few examples showing that. So here's a few examples of how you can fail to be differentiable. Perhaps your function has a sharp corner or a cusp in it. So let me just draw an example of that. Maybe your function looks something like this. This has a very, very sharp cusp right here. That is where the function is not differentiable, because if you tried to find the tangent line, you would get different results depending on which side you're approaching the limit from. How about if we have this situation? A discontinuous function would be not differentiable where it's discontinuous. So if this is my function, then it's not going to be differentiable at this point right here because it is discontinuous. We just learned that if a function is differentiable, then it is continuous, and so it can't be discontinuous and differentiable. And one other possibility of how it can fail to be differentiable is if you have a vertical tangent line. So that would be something that looks sort of like this. So right at this spot right in here, I would have a vertical tangent line. So that derivative does not actually exist. It's undefined because it would be an infinite derivative at that point. So all of those are examples of how your function can fail to be differentiable. So now we know quite a bit about derivatives. We know how to find the derivative of a function and write it as a function itself. So my question would be, can we take the derivative of a derivative? And the answer to that is absolutely we can. That's how we get higher derivatives or higher order derivatives. Our second derivative which we use the notation f double prime, or we use the notation d squared y over dx squared. That just, the twos are telling you it's a second derivative. This is the derivative of our derivative. So if you're asked to find a second derivative, you just take the derivative and then take the derivative of the result. Similarly, your third derivative, which is f triple prime, or the other notation, is the derivative of our second derivative. So how many of these derivatives can there be? Well, you can have infinitely many of them. So in general, let me write down the notation for our nth derivative. The nth derivative, the notation is either f with a little n in parentheses up there, just because you're not going to write a whole ton of apostrophes up there. After about 3, you usually just start putting the number inside of parentheses. The other notation would be a dny over dxn. That is the result of differentiating, taking the derivative, f n times. So you take the derivative, and then the derivative of that, and the derivative of that, until you reach the number that you're asked to find. So we're going to do an example finding the second, the third, and the fourth derivative of a function. So find the second, third, and fourth derivative of the function f of x equals x to the third minus x. So the first thing we're going to have to do is find the first derivative, f prime of x. The good news is, if you've been paying close attention, we already found the derivative of this earlier in the video. So we should already have somewhere in our notes that the derivative f prime was 3x squared minus 1. So I'm not going to rederive that because it took quite a while, and we'll just find our second, third, and fourth derivative from this result. So my second derivative, I know is the derivative of my derivative. So I need to do a limit as h approaches 0 of my f prime of x plus h minus my f prime of x all over h. So I'm going to plug in x plus h into my first derivative, and then subtract just my first derivative all over h with a limit in the front. And so now you would have to simplify this by doing all of your distribution and combining your like terms. So I get f double prime is the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all over h. And when I combine my like terms, I notice that some things disappear. And we get that our second derivative is the limit as h approaches 0 of 6xh plus 3h squared all over h. And just like all of our previous problems, let's factor out an h from the numerator to cancel the h in the denominator. And I get that my second derivative is the limit as h approaches 0 of h times 6x plus 3h over h. Cancel our like factor to get that the second derivative is just the limit as h approaches 0 of 6x plus 3h. Now when I plug in that h equals 0, that 3h is going to disappear, and we get that our second derivative is just equal to 6x. So there's my second derivative. And we still have to find our third and our fourth derivative. Let me write down our result. F double prime, our second derivative, is equal to 6x. And now let's find our third derivative. My third derivative, F triple prime, is the derivative of this result. So I would need to do a limit as h goes to 0 of my second derivative with x plus h plugged into it, minus my second derivative, all over h. Now I need to simplify this. When I distribute on the top, I get 6x plus 6h minus 6x all over h. Combine our like terms to get that our third derivative is equal to the limit as h approaches 0 of 6h over h. And I can cancel my like factor of h. So when I cancel that like factor of h, we have a limit as h approaches 0 of 6. And if I plug a 0 in for all my h's, nothing changes because I don't have any h's left. So I just get 6 for my third derivative. So let's write down that result. My third derivative is 6. And now we have to find our fourth derivative. So the fourth derivative is just the derivative of the third derivative. So my fourth derivative is equal to the limit as h goes to 0 of my third derivative with an x plus h plugged into it, minus my third derivative, all over h. Notice that when I plug in x plus h to f triple prime, nothing changes. I still get 6. So when I simplify this, I combine my like terms in the numerator before I take the limit, and I get a limit of 0 over h. We can simplify that. 0 divided by anything is 0. So I get a limit as h approaches 0 of 0. And so we don't even have an h to plug that 0 into, and we just get a result of 0. So this means that my fourth derivative is equal to 0. Now take a look at these derivatives here. And remember our first derivative was 3x squared minus 1. It seems like each time we take the derivative, we get something a little simpler to work with. And for polynomials, that is very true. We had a polynomial on this problem. So eventually, with a polynomial, you're eventually going to reach 0 if you take enough derivatives. So why do we care about these higher order derivatives? Well, remember that we said that the derivative of position was velocity. So the second derivative of position would be the derivative of our velocity. The derivative of velocity is equal to acceleration. That's one reason to care about higher order derivatives, is we'll be able to figure out the acceleration of particles as well as the velocity of the particles just given the position. So acceleration is the second derivative of the position function. for you on this video for today. I hope you enjoyed learning the definition of a derivative and doing those very tedious limit calculations. Stay tuned in our next video. We're going to start learning some quicker derivative rules that will allow us to not do these limits every single time that we need to take a derivative. It makes it much, much quicker. So I look forward to sharing that information with you shortly. If you have any questions, feel free to drop them below, or you may contact me through email or office hours if you are a current student of mine. And I'll see you next time.